absolute value of QC over the absolute value of the work, or in other words, QC divided by QH minus QC, everything in absolute value elements. And the way that we schematically represent that is now instead of taking heat from the hot reservoir, we're taking heat from the cold reservoir, which runs against the sort of normal state of things in terms of thermodynamics, right? If we just left things by themselves, this wouldn't happen. But we're removing QC from some cold reservoir, TC, say for instance the inside of your refrigerator. And in order to do that, in order to remove some of that heat and send some of that heat up to the hot reservoir, over here at TH, so we're moving QH out to TH, we have to input some work. All right, so we also have to do some work in order to do that. And so we have to input work in order to do that and have that process work. We can't just take heat from TC and send it on TH. That runs against, I'm sorry, guys. Oh no, I thought you were turning my attention. My mistake. So that runs against the sort of normal heat transfer that we would get in most situations. So it's not possible to do that without adding some work to the system. All right. So one particular cycle that one particular sort of theoretical heat engine that we or cycle or thermodynamic cycle that we described also was called the Carnot cycle. And the Carnot cycle is a cycle of isothermal, alternating isothermal and adiabatic processes between two temperatures. So you could represent that on a PV diagram like this. So I'm going to try to draw it well. Probably not do a great job, but we'll see what we can do. Yeah, this is not the most fabulous drawing, but we'll live with it. So this is A, that's B, that's C, and that's D. And so from A to B would be isothermal. From B to C would be adiabatic. From C to D would also be isothermal. And from D to A would again be adiabatic. Right? And we would go through that process by traveling around this in a cycle, traveling around through these four states in a cycle. And the idea is to minimize the amount of work done, right, in order to get, maximize the amount of work done and minimize the amount of heat lost, right? And so in an ideal situation, our efficiency for a Carnot cycle could be best, or sort of idealized, non-realistic efficiency for a Carnot cycle will be 1 minus Tc over Th. So you want to make Tc and Th very close to each other, so that you're going between two temperatures that are very close to each other, and therefore, very far apart from each other, in order to get the highest efficiency. In other words, you want Tc to be much, much less than Th, but it's difficult to do that with an isothermal adiabatic process. Okay, so those are all the. I realized I left my pen out of thermodynamics up there. So those are all the different things in thermodynamics that I want to cover. So hopefully that gives you a reminder of things that we did early on in the course. We're going to move on to electricity and magnetism. So we'll start off with electrostatics. So, electric charge is a fundamental property of materials, right? And some things have positive electric charge, some things have negative electric charge, and then there's some things that are neutral. We didn't talk too much about the neutral things because we're mostly interested in the things that do have charge. But what we did find out, right, is that if something has a positive charge and something else has a negative charge, then they attract each other. However, if we have two things that have the same charge, then those things will repel each other. So I've just drawn pluses and minuses, right? We don't necessarily have to have a proton and an electron for our plus and our minus, right? We could have something that has more charge than a proton or an electron. We might have some particle that has, we might have, for instance, like an alpha particle, which is the helium nucleus with 2 neutrons, which has 2 protons in it, right? So we could have some charge that's different than just the proton and electron charge. But we're not breaking things down into quarks here yet. We're not that far in physics along. But essentially, those are the fundamental quantized elements of charge in the universe, right? We're only going to find integer numbers of protons or electron charges, right? You're not going to find some charge that has 1.5 times an electron or 1.5 times a proton's charge. That's not going to happen, right? You're always going to find integer numbers of those charges, positive integer numbers of those charges. Okay. The other thing is that we can describe an electric field based on each of these charges. If I have a positive charge, I can describe an electric field which extends outwards from that positive charge. And is describing essentially what would happen if I put a positive charge near this positive charge, and it's going to tend to be repelled, and so it's going to tend to travel away. So the direction of the electric field lines, so these are electric field lines, is always in the direction that a positive charge would travel if I drop it into that electric field. Right? And so likewise, if I have a negative charge, then my electric field lines all point towards the negative charge, because if I drop a positive charge near a negative charge, it's going to be attracted. Right? Okay. And so that's sort of graphically how we can represent electric field. If we want to actually represent it mathematically, then we've got to do something with Coulomb's law. And Coulomb's law actually just describes the force that one of these charges would feel. And so it's given by 1 over 4 pi epsilon 0, Q1, Q2 over r squared in the r hat direction. And so I've got 2 charges, Q1 and Q2. They're separated by some distance r. That's given by the r in the denominator of that term, r squared, right? And then the force acts along the r direction, so it acts along the direction between these 2 charges. Now, so this describes both the force on charge 1 due to charge 2 and the force on charge 2 due to charge 1, right? So depending on which charge you have, the r vector switches in such a way that if they're attracting